This is a production of Cornell University.
Usually when you give a talk, you try to connect yourself to the place. Like, oh, the last time I was here was 15 years ago when I was skiing and whatever. It's like the last time I was here was when I came in this morning and went up the elevator. But anyway, it's really nice to be talking to a familiar group of faces. And this is some work that's been ongoing for several years. A little bit of it will be familiar to those of you who saw my talk when I interviewed here in 2012. And that was an eventful time in the Boulder, Colorado. I was there for the summer of 2012. And this is the picture I took when we were evacuated from the Mesa lab, which doesn't show up well, but it's right here, in June during the big wildfires. This is the same month when a lot of Colorado Springs was devastated by wildfires. We actually saw the lightning strike that started this one. I was on the top floor of the Mesa lab. I had office mates who had westward-facing windows and doors. They opened up the doors to go out and look at the big smoke because it was starting to accumulate, and then the wind started to change, and then it started to blow smoke into the offices, and then the loudspeaker came on, the announcement that we needed to evacuate the building. I took this picture on the way down from my bike on my iPhone. Later that summer, many of you will be familiar with the drought. At a wedding in Iowa. They were calling it the Great Corn Apocalypse of 2012. And this is a picture of what some of the effects look like. After all this, end of the summer, getting back after being evacuated into the lab, my advisor at the time, Clara Desser, who's a climate scientist, works at Mesa Lab, asked me, she knew I was working on mega drought, prolonged drought, and she asked if what we were experiencing in 2012 was a mega drought. And of course I wanted to give a really good answer. So I was like, yes, no, maybe. And I should have said what I realize now, what I should have said then was, ask me in 35 years. Because mega drought, the definition is really dependent on this time scale of a prolonged period of aridity. And the question remains, people still want to know, are we in a mega drought? In particular, when your position is extreme weather during climate change at Cornell University, people ask you, is it a mega drought? I have a good answer. Wait 32 years. Get back to you. So this is current conditions. This is probably going to weaken a little bit. This will abate a little bit with the big giant rainfall events that are happening right now in the southeast. The west is very dry, anomalously dry, as you can see. And the definition, I'm using the Wikipedia definition because I think I know who wrote it. And it captures a lot of what the scientific literature up till recently has been saying about this term, mega drought. I'll let you read it yourself. I learned something interesting about the world of the internet when I gave a talk at AGU a number of years ago about mega drought, and I read my definition out loud. So therefore, you can quote a professor saying that they constitute a threat to civilization. If you are USA Today. So graduate students in particular, be careful what you say. Historically, that's an accurate statement. Prolonged periods of aridity in the past, over the past millennia or two, have been linked to the demise of some very famous pre-industrial empires. Now, does that mean they're a threat to civilization today? Very different question. Let me just go over some other events that are noteworthy because they have been, either correctly or not, they've been labeled or attributed to being mega droughts. There's the Dust Bowl, which is about a decade, 6 years of really bad drought, a decade total if you look at the average. On this, we've got the Palmer Drought Severity Index on the y-axis plotted downward, and the duration up here, and then the size of the dots that I'm going to show is the spatial extent. So these have all been events that have, in some published literature, been termed mega drought, or at least prolonged drought. Australia's Big Dry. It's a little bit smaller, a little less severe, but still very consequential. Amazon drought of 2005, and also you could add 2011 to this. It was similar in scale, I think, and it was not very long-lived, sub-annual, but it had a strong impact on fire and carbon in the area, as I understand. Dried down a lot of the forest, and it was related to, I think, a prolonged dry season, just a very badly timed wave in the atmosphere that pushed out the moisture for an extra few weeks, leading to the drought. But it's short-lived, very short-lived, and big. And then the big granddaddy of them all is, of course, the Sahel drought, which was very consequential for parts of Africa, and the effects are probably still being felt in the region today. So there's this distinction, maybe, that had been made, still gets made in a lot of high-profile papers on this, between what we would kind of probably call drought versus mega drought. On the drought side, you might have things like, the 2012 event, short-lived. But then when it starts to get out to being really impactful, headline-grabbing, it's very attractive to start calling it a mega drought. It's a very compelling term to use a drought that is having a very strong visible impact. And so there wasn't, the line is very blurry. And the line is blurry because primarily the term is a compelling word to use when you're trying to get grants funded and papers published. We tried to be a little more quantitative. We looked, we actually started looking at this, even multi-millennial scale periods of dryness in the Southwest, other parts of the world, happening on, during the ice ages, right? You've got thousands of years where climate just dries up. Those multi-thousand-year events were being called mega drought in some of the papers. So you've got, 6 orders of magnitude in time being covered by this blanket term, mega drought. When I talk about mega drought, and in this talk and in the stuff that we've been doing, when I'm talking about mega drought, I'm really thinking about multi-decadal drought, multiple decades. Anything shorter, like 1 decade, try to call decadal drought, and a lot longer than a few decades, and we have to start thinking about whether or not it's driven by climate change, either natural or unforced, but climate change, not necessarily an interval that is dry for a period of decades and then returns to being normal. And because we're talking about events that unfold, that evolve over multiple decades, they're really at the edge of all the different types of observational apparatuses or methods of inference that we have. So we don't have historical records going back thousands of years. And we certainly don't have satellites going back for more than just a few decades. So this is a schematic diagram that I put together. And you can see the time scale here. And think of this as like the quality of the data, the resolution of the data. The precision is what I'm calling it here. So for satellites, you've got a lot of detailed information, but only for a few decades. Instrumental data, the data is not as spatially complete, but it's still pretty good. But you can't quite go down, maybe in all cases, everywhere globally to the same high frequency end of the time scales. You can't go down to days in most cases with observational data globally. And then there you've got drought and you've got weather as events that happen. We move out to study mega drought. Some of the best evidence, and I'm going to talk about this today, comes from paleoclimate archives for the fact that they've happened in the past. And then at the very top here, the global climate models, you could say, are legitimate on these timescales. They're being run with boundary conditions designed to simulate the natural variability in the climate system over the last millennium. And they're certainly able to generate data on timescales of days all the way out to millennia. And there's no problem with measuring the variables that are simulated by a climate model. They're directly simulated. But they are, at best, approximations of reality. My colleague who likes to call them Earth-like planets. These global climate models are Earth-like planets. They have many. I'm glad I made. Thank you, 3 people. And then we've got climate change, all the way out here on the top, which is unfolding over centuries. And mega drought is really right here, where you can try and use the different types of methods of inference, the different data products available that are legitimate on these time horizons to say something about the characteristics of these events in the past. So you've got proxies, paleoclimate archives like tree rings, instrumental data, and GCMs. And wanted to show some pictures of decadal drought. Most salient example, of course, the Dust Bowl in the US. This is April 14th, Black Sunday, I believe. Right? Black Sunday, April 14th. You can see this wall of dust moving in. It's catastrophic. People who've read the book, The Worst Hard Times, or seen the PBS documentary, Ken Burns, will be familiar with the idea that the dust was killing people. Infants and elderly people in particular were very seriously affected by the dust. It caused a type of pneumonia called dust pneumonia, just from the inhalation. It's really, really damaging. I don't need to tell you guys this. This is when I'm talking to climate scientists, I say this. All right. 1950s, this is a picture from the 1950s drought. Lesser known, maybe not as visible, salient example, but certainly very painful for agriculture, for farmers and growers who lived in the Southwest during that time. In fact, after some of these studies came out, I got an email from a Cornell alum saying that his family has been growing crops in Texas. Remember the 1950s being really, really bad. Multi-year intervals of aridity that were really, really bad. And that's all in my bin, in my notion of drought, the bin of decadal drought. If you go up 10 years in either direction from these events, you're not really seeing the same effects as during that decade of drought. It also lends itself to a pretty convenient method for detecting decadal and multi-decadal droughts. Because if you just look at the precipitation anomalies alone, pick your favorite index, favorite drought index, and there's lots of them, and they lead you to a similar story. But just take precipitation alone. Right here, we've got, in gray, precipitation totals in the Great Plains. So annual averages. In black is a smoothing curve, like a 10-year moving average. And then here we've got 1/2 of one standard deviation, and you can see that the black curve stays below 1/2 of one standard deviation for the entire period of the drought. It's an objective metric that lets us pull out these things from data. Apply the same thing, and you can see the same type of threshold applies to the Southwest drought in the 1950s. So just as a starting point for a definition of a drought that we know would be bad, would be as much of a precipitation deficit that we saw during the 1950s and 1930s, this works. 1/2 a standard deviation in the long-term average, the 10-year average, seems to identify these intervals and not spuriously identify other intervals, which is good. We've got precipitation, we've got moisture, we've got tree ring measurements we can try to apply this to. It's a picture of Connie Woodhouse right there, up on a mountainside in the, I think it's the San Joaquin Mountains in southern Colorado, coring a tree. I got to go out with the tree ring folks only once, when I was at the University of Arizona doing my graduate work. And I think I was able to core about 3 trees in the time that one of these superstar dendroclimatologists cored like 24. And I was super sore the next day. You go on these Swedish coring devices and cranking, and it's exhausting work. I mean, maybe some of you do it. I always thought I was really like in good shape too. Like, I'll go to the gym, I can go out there and core trees with these dendroclimatologists. No, they're zipping up and down these like 45-degree slope mountains on scree and drilling out cores of trees at a rate that is it's impressive. It's very impressive. At the time, when I was at graduate school at the University of Arizona, the world-famous tree ring lab, dendroclimatology, was right underneath here. In the stadium of Arizona, the Arizona football stadium. And I was persuaded upon by a good friend, colleague, Scott St. George and Kevin Anchikaitis, both of who had finished a few years before me, to go and see if I could convince Dave Miko, who's a world-famous dendroclimatologist, who's someone in the room I know has worked on with various papers and proposals, convince him if I could do a study abroad in his office across campus in the dendroclimatology lab. It's very convenient on a Saturday if you're working on a Saturday, and you want some nachos. You just go right across the hall and get your nachos from the concession stand, and then go back to work. And of course, this is like rich, woody smell in all the labs and in all the offices. And the guys that work there have these big beards. They've been doing it forever. And you feel like you're in Lord of the Rings. I mean, you feel like you're just surrounded by ants or some mythical creatures that go out into the forest with superpowers and bring back climate archives. And so one of the things that I learned about when I was there, I was very interested in this idea of how well can we make inferences from tree ring data about low frequency variability in hydroclimate, and how might that inform our understanding of drought statistics, particularly mega drought statistics on these multi-decadal, even multi-millennial time horizons. So you go into the field in the summer and drill a bunch of cores, which look about like this, bring them back to the lab, measure the ring widths, and then they usually just get plotted up to begin with as ring width measurement indices. They're not even indices, they're just ring width measurements. So this is just raw ring width from what? 1, 2, 3, 4, 5, 6 different trees. Nothing has been done to massage the data. It's just what you get when you get back to the lab and you spend your time measuring up. There's also a very important step that gets overlooked and has been overlooked in some very high-profile, high-impact papers. It's important to understand, and it's how these things are aligned in time. It's a very quantitative, very precise science. And sequences of relatively wide and narrow rings are very good indicators of a time period. They're like a barcode. They're unique, and they can be used to match where things must align in time. And they have been, and they're also very effective for identifying places where growth is missing during a year. I'll be happy to talk about that after the talk. But the main point here is that in this case, most of these actually ended when the tree was sampled, and then you can just count time going backwards on the x-axis here. Raw ring width measurements. Typically, one then tries to model the non-climate influences on tree ring growth. This is important. I'm going through it in a lot of detail because it's really important to our understanding of mega drought, fundamentally, overall. In this case, I fit a spline, just a smoothing curve, to the ring width indices to try to estimate the non-climate sources of growth. Typically, splines are set to be removing 100% of the variance at 2/3 the length of the segment. Other more stiff splines might be something like a negative exponential that models growth as being very sharp in the beginning and then decaying rapidly. Other ones still are more flexible. The latest and greatest best methods, best practices for detrending try to estimate the growth from each individual site as a residual once you factor in the total cumulative growth across sites, if that makes sense. There's lots of different methods, and it's really important on the long time scales to get it right, or at least to be able to quantify and understand what you're missing or what you might be missing and what you're removing. Because typically, you're chopping out the low frequency end of the spectrum. You're chopping out the low frequency variability. If for no other reason than, in the simplest possible case, a tree is putting on the same amount of carbon each year, but because its radius is getting bigger, the width of the ring has to get smaller. There's more going on in real trees, right? There's biological processes. They shift away from using resources to grow towards using resources for reproduction. So there's all kinds of non-climate sources of variability on these multi-decadal to century timescales that need to be accounted for or factored in or investigated if we want to get at this problem of mega drought. Once that's been done, you usually do a detrending using those splines. So imagine subtracting that. There's a second step that's often applied to standardize them to unit variance, and that's what we've got here. So these are ring width indices now, not measurements anymore. They've been detrended and standardized to be ring width indices. And this is just a subset from one site, I think in the San Joaquin Mountains as well. Usually there'll be a few dozen trees going into a compilation of ring width indices. You make a compilation of ring width indices, you've got tree ring chronology. And that's what I've done here, just for illustrative purposes. The chronology, it's like a weighted average or an average of the individual constituent ring width indices via the central limit theorem. And it's important to factor in our understanding of hydroclimate in trees that these sites have been pre-selected to be moisture sensitive. You're in the Southwest. They go out to parts of the mountains where it's very likely that moisture is the limiting factor on growth. You go too high up, it's probably temperature. You go too low, well, you're in cactus. In the Southwest, in this middle zone, you got long-lived trees, and moisture is the primary limiting factor on growth, which gives you a good chance at being able to reconstruct moisture variables like the Palmer Drought Severity Index, like precipitation, like Colorado stream flow. And those reconstructions now are derived from sets of chronologies. So dozens of ring width measurements go into making ring-width indices. Ring-width indices are then averaged together to make chronologies. Chronologies then are used to do a single reconstruction. Again, via the central limit theorem, we hope this all works out, but it might not work out the same way on different timescales, and that's something that's an active area of research. In the case of the Colorado River, this is from Miko et al., 2007, the same Dave Miko I shared an office with for a little while. It's the reconstructed flow as a percentage of the 20th century mean. So 100% be 20th century mean. Very famous figure. This is probably one of the most widely used paleoclimate results out there. Observed flow in black. This is the 25-year running mean. That's the thick black line. The thin black line is the smoothing, same smoothing, 25-year running mean of the reconstruction. The gray shading are the confidence limits. And what you can see is this event back in the 1150s, among others, drops below 87% of the 20th century mean for at least 1 year. And actually, in the case of 1150s, it's about 11 years. Now, this is not a great definition of mega drought. It's very hard to communicate that we're talking about the an interval that's characterized by an 11-year drop in the 25-year running mean at 87% below 20th century averages. So we tried that definition for a while. We had a bunch of papers rejected with that definition. So we tried to simplify it, which is why I introduced the other one that we're going to actually use for this analysis. There's one event that satisfies those criteria. 11 years below 87% of the 20th century mean and the 25-year running average. There's one event, and it's the 1150s mega drought that's been incorporated into a lot of decision-making about how to use water resources in the Colorado. And if you just look at the point when flow gets that same 87% threshold, there are a few other intervals. And these have all been called mega drought. I would call them decadal drought. Maybe that 1150s drought qualifies as a mega drought, multiple years, 25-year running mean. And we can then look at other hydroclimate reconstructions from the same region. Up here, just pulled out all those places that I circled before to show you these decadal droughts. And they're happening at about a rate of 1 to 2 times per century. It's a good benchmark. And if you look at some of these other reconstructions, this is the Palmer Drought Severity Index, also reconstructed from trees, also for the Southwest. They're not completely in sync, even though it's a similar region, which is interesting in and of itself. But you do get a similar rate, 1 to 2 of these decadal droughts per century. This is from Staley et al., 2011, also a PDSI reconstruction from northern Mexico now. And it's important, again, to notice that it's not like these events are lining up in time. So there is maybe an inherent spatial scale. There's information there that we can use to try and understand the nature of these prolonged droughts. All right, and then if we go back even further, apply a more rigorous smoothing, look for intervals that are below this -5 standard deviation, negative 0.5 standard deviation in the running mean, the 35-year running mean, there's really only 3. The NADA is the North American Drought Atlas. And this gives us an answer to a question that a lot of people have been asking for a long time. And I think the first paper to address this was in 1998 by Jonathan Overpeck. He was one of my advisors in Arizona. And their answer back in 1998 to this question of how likely are megadroughts from a paleoclimate perspective was that decadal droughts looked like they were occurring about once or twice per century, perfectly consistent with our idea of the 1930s Dust Bowl as well as the 1950s drought in the Southwest. Decadal droughts occurring once or twice per century. And these multi-decadal megadroughts now, multi-decadal megadrought, 35-year interval, 35-year period of aridity, maybe 1 or 2 per millennium. Very rare events. And these statistics seem pretty much to hold up. There's initial estimates from 1998 held up pretty well with our more quantitative analysis of more data. Ended up in the same ballpark. Now, to get at the likelihood of megadroughts, we want to know something about the past from the paleoclimate perspective, from tree ring width measurements, tree ring width indices. We also want to know something about the underlying statistical characteristics of hydroclimate in the region. And a really convenient tool, especially for comparing with models, is the power spectrum. And specifically the color, quote unquote, of the power spectrum. So if we've got time scale here on the x-axis and amplitude, some hydroclimate variable, PDSI, stream flow, a red spectrum is going to have generally more variance on the time scales. White would be like a uniform distribution of variance across time scales. And blue, which you don't see in very many natural systems, but you do in some of these Earth-like GCMs. A great example of this is the Community Climate System Model 3, so a couple generations ago. It would give you an El Nino, La Nina cycle every other year. So it'd be El Nino, La Nina, El Nino. It's like a ping pong ball being batted back and forth from one side of the table to the other. Well, if you're sampling that at an annual resolution, you're going to get this big peak right at the Nyquist frequency. And that would be like a blue power spectrum, where the variance is pushed away from the long time scales and concentrated at the shortest ones. So in nature, they're, I guess, relatively rare. I think the people who do seismic imaging have to worry about that kind of a spectrum. But they're relatively rare in nature. This was a paper, result from a paper from Hoybers and Curry in 2006. Very important, very significant paleoclimate result, where they looked at the power spectra of temperature, so not hydroclimate per se, but temperature across, several orders of magnitude. So from seasonal all the way out to millennia, multi-millennial. So we're talking from Milankovitch down to seasonal timescales. And they argue that there's this just general redness, steepness to the spectral slope that's positive for temperature up to century-long timescales here. There's some inflection point, and then you go down into more of the sort of the nonlinear Brownian motion regime, which is really potentially very interesting from a long timescale climate dynamics perspective and may have some implications for climate change. And I was really just interested in adapting this whole framework to hydroclimate to ask if we could come up with a similar type of diagram from hydroclimate proxies and compare them with temperature, to compare the power spectrum of hydroclimate. Because presumably, if you have very red power spectra and power spectra that are red on long time scales, that would mean something different about the risks of mega drought, because you'd be able to stay in a dry regime for a long time, because there's a high amplitude at the low frequency timescales, versus if you have a white or a blue power spectrum. And one thing, though, that makes this a little more complicated for moisture, soil moisture, and other archives of hydroclimate as opposed to temperature is storage. So the Hoybers and Curry paper is able to get away with using very coarse resolution proxies that are geochemical, that have relatively small basins to worry about with mixing timescales of maybe a few decades or even a few hundred years. Or even if you're if you're looking at the Cariaco Basin, you're worried about the whole ocean, you still are only worrying about a few millennia, and they're going out to hundreds of millennia. Whereas for mega drought, for decadal drought, we do have to think about what effects are we going to have of the sensor, the tree ring measurement itself, on the distribution of variance, the power spectrum. And this is a simple idealized drawing where you can imagine some white noise input being filtered through the proxy, the tree ring width being a function both of annual moisture availability, but also previous year's growth, in situ soil moisture, a host of other factors that are going to smooth out those high frequency fluctuations and emphasize the longer timescales. And the simplest model that probably one can come up with to try and quantify this effect is this first order autoregressive process. So you've just got your proxy at time t, some autocorrelation coefficient, and noise. And we can investigate this using the Palmer Drought Severity Index, which has a prescribed autocorrelation coefficient of 0.897 from 1 month to the next. So it's not 0.9. It is 0.897 from 1 month to the next month. And we can use that to calculate an analytical power spectrum and do Monte Carlo simulations of PDSI to get at the range of amplitudes that one could predict on these longer timescales solely from autocorrelation and a white noise background. So if there was no other show in town in the Southwest besides weather and autocorrelation, this is the power spectrum we would predict, analytically in this black line, and with Monte Carlo realizations in the gray shading. It's a very nice benchmark, then, against which we can compare our collection of hydroclimate proxies, in the style of Hoybers and Curry, and hydroclimate proxies now in the Southwest. So up here, we've got in the colored lines different tree ring reconstructions. Reconstructions, all of them, all available reconstructions of all stream flow variables in red, all precipitation reconstructions in purple. And then this is a really pristine, or really high quality, very carefully constructed data set that Connie Woodhouse and her colleagues put together from the 5-needle pines in the Southwest. And it was designed to have the best chance of preserving those low frequency timescales by only using long segments. So at the stage where you're building a chronology, they threw out anything that was shorter than like 200 years or 250 years. So right off the bat, you've got a good chance of having long segments which are required because of how the detrending is applied. You need long segments. You already got long segments, and then they also additionally applied very conservative detrending. So trying to leave in as much of that low frequency variability as possible while still removing the non-climate factors. The other archives on here are non-tree ring. So the symbols are non-tree ring proxies from lakes and caves, and then the gray line is their average. And there's some things that are a little surprising and some things that aren't very surprising in this diagram to me. One is that, for the most part, the tree ring records on these cases is about a decade, a century, a millennium. Most of the tree ring reconstructions, other than this 5-needle pine, very pristine data set, are well within the confidence limits. It's a really significant result and a really problematic one for lots of reasons. It means that for most of the stream flow reconstructions that we have, the emergence of mega droughts, of decadal droughts at least, is not outside of what you would expect from stochastic forcing plus a little autocorrelation and a bunch of time. Right? You're right in the middle there. But you have these other proxies pointing at a different story. And we know that there's some detrending applied to these, when the variance dropping down here is maybe indicative of that the detrending itself is removing variance in these long time scales from these other reconstructions, whereas in the non-tree ring reconstructions, non-tree ring proxies, there's no detrending. And they're all giving you this kind of red shape that's aligned fairly well with the 5-needle pine database. So I think the weight of evidence from this diagram is towards rejecting the null hypothesis. In other words, it's not that the only show in town is autocorrelation, stochastic forcing, and a bunch of time. There's something more interesting happening on these longer time scales, driving the low frequency variability. We reject the null hypothesis. With more data, we probably will have to revisit this whole paradigm. But for now, it doesn't seem like we have any reason to think that the variance out here in these proxies is driven by something other than climate processes. So we want to do this purely from statistics now. We've got different noise models that we could apply based on the autocorrelation or low frequency behavior of the paleoclimate archives we have, try to reproduce their variations through time statistically, and come up with an assessment of prolonged drought and mega drought likelihood. And that's what we did in one of these papers, where we just looked at white noise, AR1, and then a power law distribution in frequency, power law distribution, to try and get at this long time scale, high amplitude tail in the power spectrum. What's really cool, I think, about this figure is that the way that we constructed our methods, you can compare in time the different types of noise models. And on short time horizons of 50 years, it almost makes no difference. You're getting the same kinds of statistics. And they all have the same exact variance, zero mean. On longer time scales, when you were only looking at the interannual fluctuations, you'd still, even if I wasn't using gray shading here to save money and Journal of Climate publication charges, which are sizable, even if I wasn't, you'd still be hard-pressed to tell the differences. But then when you smooth, you look only for the low-frequency components, the power law distribution has this persistence that really pops out. And so you stay away from the mean, both above and below the mean, for longer, when you're looking at the power law distribution, which is what you'd expect, but that could be important for trying to characterize the risk of megadrought. And indeed, it matters quite a bit. So these are just different PDFs, different ways of looking at these Monte Carlo simulations to characterize the risk. Number of years spent in a decadal drought risk as a fraction of all 50-year periods experiencing one of these events, and multi-decadal megadrought risk. It really matters out here when you get onto the multi-decadal megadrought risk. If the system were fundamentally white in nature, if it was a white noise process generating droughts, you would have only like a less than one, I think it's like 0.4 or 0.3% of all 50-year periods actually had one of these 50-year or 35-year multi-decadal megadroughts. Very, very rare. AR1, they become a little more common. And power law, you can't quite ignore them. 15% of all 50-year chunks had one of these 35-year megadroughts in them. So this is a purely statistical, probabilistic approach to the problem. And it gives you an answer. Actually, these two are more or less, both of them, consistent with the paleoclimate estimates of 1 to 2 decadal droughts per century and 1 to 2 multi-decadal megadroughts per millennium. There's a consistency there. So then the final thing that we looked at, that we're interested in using to come back to this question of how likely are megadroughts in the future, are global climate models. Not only are they able to be run for hundreds of years in standalone mode with boundary conditions set to pre-industrial levels, which could give you a nice benchmark in and of itself, they also are, of course, being used to assess and plan for climate change occurring from human activities this century. They're the crystal ball into the future. And we have no reason to think that the statistics of the past, whether these are inferred from paleoclimate archives or statistical models, Monte Carlo methods alone, we have no reason to think that those should be stationary into the future when we're changing climate. And if we're changing climate very significantly, there's very, very little reason to expect those ratios of 1 to 2 per century for the decadal drought and 1 to 2 per millennium for the multi-decadal megadrought to hold up into the future. So that's why we need to look at the GCMs. It's a requirement for trying to get it right for this century. I think everyone's pretty familiar with the idea of a GCM. It's a global climate model. What I will say about them is that when I was at NCAR, I think in my second year there, the chief software engineer for one of the groups I was working with was suddenly put in his 2 weeks notice and was gone. It's gone. He was recruited by DreamWorks. Became an Imagineer. So why did DreamWorks want a software engineer from NCAR? Well, DreamWorks is very interested in computational fluid dynamics because when Shrek sails off into the ocean, they want the ocean to look realistic. And doing it in a way that looks realistic means solving the equations of fluid flow numerically in a plausible way that our own intuition will tell us looks good. So that's why people like the chief software engineer, the group I was working in, gets recruited by places like DreamWorks. Also, I think they pulled up a dump truck of money and told him to get in. I think that was part of why he disappeared so quickly. So it's the same set of equations that one uses for video games, for Pixar, for DreamWorks, solved differently, of course, in 3 dimensions on a grid across multiple layers in the ocean and the atmosphere. And it does all of the exchanges of heat and energy and mass that are important for the whole climate system. These are results from just one model running out into the future. I'm sure you've seen these kinds of diagrams before, where you've got the different RCPs, representative concentration pathways. Down here on the low end, optimistically, if we avoid the worst effects of climate change, we're down here on the low end. If we just burn, baby, burn, we're going to end up on the RCP 8.5. Actually, if you look recently at the most up-to-date estimates that I could find on what we're actually doing compared to the RCPs, people seen this? We're slightly, just a little bit above the worst case scenario envisioned in 2007. So we're up here somewhere. Bottom line is, the higher the number of the RCP, the more warming we expect because there's more radiative forcing. And this is I don't want to go into a lot of model bashing. I mean, I love climate models, but there are some serious limitations that do need to be acknowledged, particularly as they pertain to the problem of mega drought. Systematic biases, very small ensemble sizes. We assume that because they're based in physics, we can get away with smaller ensemble sizes. You don't need a 1,000 or 10,000 or 100,000 realizations of a GCM if it's doing something dynamically realistic in the flow of the fluid itself. But the ensemble sizes are still very small, and the natural variability is substantial. One of the systematic biases that could be particularly relevant for mega drought is this one. They're oftentimes too wet in a lot of places in the northern hemisphere, and especially in North America, and even globally. This is the total amount of precipitation in the models occurring, just as an average in millimeters per day. And this is GPCP, so this is the observations down here at the bottom. Most of the models are a little too wet. It's a consideration. Another one that we published on a few years ago now, they have a distribution of variance as related to what I was telling you about CCSM3, the old version of the NCAR model. They are systematically too high frequency. They're pushing interannual variance around at very high amplitudes. And that relates largely to the tropical Pacific. They fluctuate between an El Nino and a La Nina state not only too quickly, but also very energetically. And when you compare the precipitation spectra, the power spectrum of precipitation from the models to the observations, it really looks like it's a big difference. A factor of maybe 5 to 10 in some cases on the long time scales. But even with those considerations, and a couple more that I'll list in a second here, we dove in head first and looked at these very cutting edge, this is still very cutting edge new area of paleoclimate simulation. Historically, paleoclimate simulations were done for, say, the mid-Holocene, 6,000 years ago, or the last glacial maximum, where you're really just interested in the mean climate you get from a fixed set of boundary conditions. The last millennium, trying to simulate decadal and multi-decadal and multi-century variability over the last millennium requires a whole different approach because you actually care about the time evolution. Right? It's not a fixed, ice sheets here and Earth's orbit looks like this. It's a time evolving forcing. So you've got volcanic aerosols to worry about, big eruptions from the past, solar variability, sunspot cycles related to total solar output. And of course, the gradual changes in the Milankovitch forcing, the shape of the Earth's orbit and its tilt in particular. And when you put them all together, these are our primary tool. And it's the best we've got. And put them all together, force the model, and just to give you a sense, here's an animation for what it looks like. This is going to be smoothed sea surface temperature. So low pass filtered, decadal sea surface temperature. Up here at the top is the total forcing at the top of the atmosphere. And the map is sea surface temperature after removing all the high frequency variability. And you can start to see some of these volcanic events showing up. I'm gonna fast forward this a little bit. We can get to the good stuff. This big 1258 eruption. All right, wait for it. It's coming. There's one. There's another. And you can already see, this is decadally ripped out the interannual variability. The frequency of the forcing is very abrupt. It's like a delta function. It's very abrupt forcing, but you're seeing it propagate out into these longer timescales. And you just happen to have this century here where there's volcanic activity and one very significant. This scales to like 25 times the Pinatubo 1993 event. It's a very significant volcanic eruption. Just to remind you, the power spectrum of the proxies looked more or less like this in the slide that I showed. We're going to make the same calculations from the models. This is all of them, all the last millennium simulations. Pre-industrial, these are unforced, but about 1,000 years long. Last millennium simulations, there's that reference line from the proxies. Last millennium simulations only through 1850, so pre-industrial portion of the last millennium simulations, and then just the 20th century. There's no, if that's interesting variability, right? It's above what you expect from the null hypothesis. There's not a model out there today that's generating that level of low frequency variability. So if it's dynamically driven, it's being generated by processes that are maybe not very well resolved by the models. On the other hand, if it's a forced response to the models, which is very plausible considering how much of an impact explosive volcanism seems to have, it's still not showing up in there. And that could be important for our understanding of mega drought. And then you've got the small ensemble size. I want to come back to this. Say this is you run 4 simulations with a model, CCSM3. You run 4 simulations. And you get this distribution of some variable. But truth looks more like this. Well, that's a problem. You need to be able to factor that in. You can see this in the terms of mega drought. You say you've got some shift in the mean, and then you've got 2 realizations of a model. In the first one, there's a mega drought. In the second one, there isn't. The mean is the same. The variance is being drawn from the same shifted mean. But you only have 2 realizations. So does that mean the probability is 50%? No. It means you've undersampled the full PDF of plausible future climates. It's a big problem we need to think seriously about. And this last one I'm not going to dwell on very much, but it's potentially a factor that we haven't accounted for, which is that code has been shared between centers, and that can have an impact on the macro scale behavior of the model. So not necessarily truly independent because they have software components that can generate emergent processes that are similar, structural similarities. Our workaround for all these considerations, we focus on changes relative to the 20th century that are in-model relative changes. Try to use Monte Carlo methods to fill out the PDF. And ongoing work, haven't really finished, is trying to identify clusters of similar models and look at the risks within clusters. So we can come back to this question. How likely, if you look at the GCM world, how likely are these mega droughts? And put it all together. 3 different forcings, RCP 2.6, 4.5, 8.5, making white noise assumptions about the underlying statistics of precipitation. You get this increase in risk that's primarily reflective of the Southwest getting drier. Come down here, we're using different noise models to emulate the statistics of the model of the GCMs themselves. And again, there's this increase because when you saw before, you use power law as your generating process, your tendency to persist away from the mean is greater. And then the combined high forcing with an assumption about power law distribution in the frequency spectrum gives you the highest estimates of risk. And this is only applied to precipitation. That's decadal, so 10-year. So making events like the 1950s drought in the Southwest, 1930s Dust Bowl look like there's 80%, 90% of the realizations seeing events like that. And then multi-decadal mega drought. So this is really the take-home from precipitation only. Doesn't even factor in the temperature effects. You've got 35-year average giving you conditions in the models that are as dry or drier than the 1930s. We're emulating this with different noise models, but in all cases, I would call this a very non-negligible level of risk. 30, 40, 50% chance that we're going to be seeing a background shift, weighting the dice towards making these events, which historically, in the paleoclimate view of the world, have only occurred 1 or 2 times per millennium. But this century, because of this shifted baseline, they're much more probable. I'm going to finish here because I need to go teach a class. And this isn't just a US. We're not alone. You look globally and do the same types of calculations. The US is just one pocket of the world that looks likely to be exposed to this very high level of risk. We turned the crank again, factoring in temperature, and it looked way worse for most of these areas. Because in dry areas, when it's hot, the demand for moisture goes up. And it goes up with temperature very, very dramatically. You can see that for the Southwest. 1,000 years in the Central Plains of reconstructed PDSI, and the future. 1,000 years of reconstructed PDSI in the Southwest, and then the future. And we're really getting away from mega drought because we're talking about climate change now. And we're talking about climate change at the end of the century. And I would say the number one feedback that we got from stakeholders and water resource managers after these papers were published was, that's great, but I can't use information about 2075. I can't deal with 2050 to 2100 being your reference point. What can we do? What's actionable now? And so I really shifted my research focus away from these climate change time horizons down towards decadal and seasonal time horizons. Because even as bleak as this picture, you'll see this in this animation, looks, brown is going to be dry. This is the future. Brown is dry. This is if we just keep on burning the rate we're burning, or higher. That's the future we have. And even as bleak as it looks, it's not actionable enough. And we want to be able to see things unfolding in closer to real time as they happen. So that's what we're focusing on now. We're focusing on seasonal prediction and decadal prediction and trying to get not at this long time scale, not at the low frequency end, but really switching several orders of magnitude down towards the higher frequency end of the power spectrum. So I'll end there because I got to go pretty soon here. Thank you.
The drought that occurred in the 60s in the New York City watershed?
Yes.
So was that like a decadal drought?
That's decadal.
And so we would expect that to occur?
Yeah, it's probably, without climate change, it would have a chance of probably 1 or 2 times per century.
Yeah.
Now, it looks like it's been getting wetter, right? So we don't know. We haven't assessed the Northeast yet.
Okay.
I used the story of that drought because my mother-in-law lived in the 60s. Lived in New York City during the 60s. And she remembers the signs in the subway that said, "Save water, shower with a friend." So there you go, lucky people of the internet. I said it. I'm on camera saying it. Yes?
Just a quick question here. Are you focusing mainly in the United States, or are you looking at the droughts in East Africa that are?
Yeah, we want to branch out globally. I think this is one of these cool things about being at land-grant university, is that the methods apply wherever we want them to, essentially. And if you have great paleoclimate records, you can do a better job. But even if you don't, these preliminary estimates are probably actionable in some cases for long time scales of water resource management. So for building dams or looking at strategic aquifer reserves, that kind of thing.
So the same short-term seasonal.
Yep.
What if you use this to plan early warning?
I think that's the idea. Yeah, ultimately to scale it out, more short-term, more actionable, and scaled out to other places that use water, which is everywhere.
This has been a production of Cornell University, on the web at cornell.edu.